So welcome all to our Magnifier presentation. Let's ask a very simple question. Where does traffic enter and leave a network? So if we have small networks, that might be very easy to answer. But moving towards larger networks or more traditional networks that do not feature things like programmable devices, it can be quite tricky to answer these, especially when focusing on networks that have global reachability, such as internet service providers. So let's dig a bit deeper into this question. If we want to figure out where traffic leaves, like the exit point or the egress, we might be tempted to say that's quite easy. We can just look at control plane data. And to some degree, that might work if we have all the routing data of the network available, but getting this data is challenging, and it opens also the question what happens during failures or convergence time, where perhaps the control plane doesn't follow, the data plane doesn't follow the control plane information. Now, if we also consider where traffic might enter the network, looking only at control plane data will no longer be sufficient, and we really need some data plane insights. Now, that opens the question how we can get insights into the data plane traffic of large ISP networks that can have transit capacities of like 30 terabits per second, as for example Deutsche Telekom reports today. So operators of these networks currently use monitoring solutions which often have some imperfection in order to scale to the amount of traffic. And here I list two different approaches. So we could consider packet sampling, so where we get some sampled flow statistics, for example with tools such as sampled S-flow or NetFlow. Or we could have packet mirroring, where we can have very specific traffic mirroring according to some rules that an operator defines. And I would like to show you some key points of these two techniques, looking at three different metrics. First, how much traffic we can cover with them, what the accuracy of them are, and how fast we get feedback from them. So if you first consider traffic coverage, in theory, sampling can give us a good coverage because any flow could be sampled, but that's not really the reality. Often we are heavily focused on the long or heavy hitter flows. On the other hand, mirroring is very precise to whatever is defined on the device, but nothing else is mirrored. Looking at accuracy, sampling, if we are lucky that we sample a flow, is great, but we might never sample the same flow again or not on different devices. Whereas if we have a precise mirroring rule installed, we would get all the traffic that matches this rule, but at a very high cost. Basically, all the traffic is doubled that matches the rule because all the traffic is cloned and forwarded to some collateral. And finally, speed criteria. What we observed with real sampled data from a large Taiwan ISP is that caching and aggregation often adds delay until the operator really sees some results of it. And we observe delays of around 30 seconds on average. Whereas we believe traffic mirroring is much more direct in the feedback we get. As soon as the packet is cloned, we get some feedback. So looking at both approaches, we see advantages and disadvantages, and we kind of concluded none of them are perfect in its own. And that made us thinking if we can somehow try to combine them or improve one with the other one. And that is the main idea behind Magnifier, where we try to combine benefits of sampled data with mirrored traffic and trying to mitigate as many of the drawbacks as possible. And in the next couple of slides, I hope to show you how Magnifier works. On the very high level, we have these different blocks or processes that happen. We first have an inference step based on sampled data, which could be wrong, and then we try to validate that using mirrored data to get some sort of up-to-date ingress and egress observations. So how does that work? In a bit more detail, the inference step first, Magnifier tries to find IP subnets that span as many as IPs that match a subnet towards the ingress or an egress. So we have some sort of connection between the traffic and the ingress or egress based on the sampled observations we have. And then we use mirroring, but naively mirroring this traffic to validate it would create a huge amount of traffic in the network in addition, just for the monitoring overhead. So instead, we do it a bit in an intelligent way and try to mirror on ingress or egress points where we do not expect to see this traffic based on our inference. So if we see no traffic, that is a good sign. Otherwise, we made some mistake before. So let's look at the first step in detail. So Magnifier receives some sampled flow observations and once again, looking at real data, we observed sampling frequencies of 1 in 1,000 or 1 in 4,000, meaning like we only get very few packets here. And the main goal of the inference step is to cover as many IPs as possible with as few subnets as possible. So to illustrate that, I will show you a very simple example where we assume we have a network with 3 border routers that could be the ingress or the egress of traffic, called R1 to R3. And now we sample a few packets, so 1 from R1 and 2 that were observed on R2. And I place them in the IP space that belongs to their source or destination IP addresses. And in the inference step, Magnifier now tries to find subnets that cover as many of these sampled packets, spanning the space around them to have a unique mapping between the IPs and the ingress or the egress. So in this example here, if you look at the green subnet, we infer that potentially the green subnet enters or leaves, depending on what we look at, over route to R2. Note that at this point, this inference could be wrong, as we have only some limited insights from the few sampled packets. We don't know anything about the rest of the IP space, or corresponding traffic could also enter somewhere else. So to validate that, we now try to deploy mirroring rules that support our assumption. Again, looking at the green subnet, we install a rule on R1 and R3. So note on the 2 ingress or egress points where we do not expect to see the traffic. So what is the idea behind that? If there is active traffic from the green subnet, and it indeed enters or leaves on the place where we expect R2, we will not get any mirror traffic. And we have very high precision that that is correct, because as soon as there would be a deviation from that, we would start to see mirror traffic. On the other hand, if there is a change, or if we did a wrong inference, the mirroring rules will trigger and generate traffic. However, obviously, by deploying them on the places where we do not expect traffic, we can also reduce the amount of mirror traffic that we get. And doing so, we get validated ingress and egress observations, and we can also go further and use the wrong inferences that we make, so the observations that we get from the mirror traffic, and feed it back to the next inference operation that we do to, over time, improve our results. So that is, on a very high level, how Magnifier works. However, there is a catch, and adding so much mirroring rules on devices actually is a limiting factor, because today's devices have limited resources, and depending on how we do that, we need to be careful that we don't use resources such as memory that is used by other router features, for example, for access control lists. So that is one challenge, and also adding and removing mirroring rules at scale can be very slow, so that is also a difficulty. Finally, if we only have one controller in a global network, it actually might take us quite some time from the first time we get some mirror traffic due to a wrong inference until we can perhaps deactivate the mirroring rule and then terminate the traffic generation. So in the paper, we give detailed ideas and solutions to some of these problems. Here, I only have time to highlight the most key points. So for the memory limitations, we have different schemes and ideas how the operator can prioritize which traffic or which ingress and egress observations or inferences we would like to validate with the available resources. While the activation time we could greatly decrease by pre-deploying rules on the device without activating them, and then activating in batches a lot of rules at once. And finally, we can have subcontrollers close to the network border. We can very quickly react to the traffic amount. Here, I would like to notice that if operators are afraid that there's too much mirror traffic generated by the system, we could always use existing features on the devices itself, which limits the amount of mirror traffic that can be generated, for example, to a certain bandwidth. And note that, in theory, one packet alone would already be enough for Magnifier to figure out that some of the inferences are wrong, so we can work with fewer traffic here. So let's see how that actually performs. And to evaluate Magnifier, we did simulations and experiments, and in the simulation and experiments in our lab, on real devices. And for the simulations, we used simulated sampling and mirroring operations and assumed kind of ideal assumptions, for example, on the amount of rules we can install on the device. While in the lab setting on Cisco devices at ETH Zurich, we had at most 500 mirroring rules on one device, which was easily feasible for the devices we had available. But we also observed that much stronger devices that are used in larger networks have much more capabilities there. So the final question is, what traffic did we use for the experiments? And here it was important for us that we had the full ground truth view on which packets there are. So we could not just use a sample trace, for example, from a real network, because that makes it difficult to see if our inference was correct or not. So we used KIDA traces, for which we have a full insight. However, there's one problem here. Now that we have one or multiple KIDA traces, we somehow have to assign the different packets and IPs we observed there to ingress or egress points in our network. And for the evaluation here, I focus on ingress point inference and validation, but similar techniques or the same results also hold for egress observations. So to kind of find different assignment strategies, we developed 3 different types. First, a random one, where in theory, the same IP can enter our network over a random ingress every time we observe it, so it's a very challenging situation. Then a static one, where we initially add every IP to one single ingress point and then keep it over time, so there's time consistency, but no consistency in the IP space. And finally, permuted, where we permute on a subnet basis, making it more prefix-like as we might see it in the internet. So in general, we believe that going from random to permuted makes it easier for Magnifier to perform the operations. And in reality, it will be a mix of all these different scenarios. So let's first look at some simulation results. And here we simulated 32 ingress routers and assumed a sampling rate of 1/1000. And this plot shows the different assignment strategies. And on the x-axis, the amount of packets for which we had a validated ingress point with Magnifier. As comparison, if we would only look at the few sample packets we get, we obviously have very poor insight, which is not surprising. So looking at the more challenging random assignment, we can already cover around 15% of all the packets and tell an operator, for example, this IP would enter here in your network. And that is much better for static and permuted assignment strategies where we can reach up to 77% of the traffic. Now, that is simulations, and we also looked at the mirror traffic. Given the very perfect conditions of the simulations, it was very low, which obviously does not hold in a real deployment, but here it was basically negligible. So let's see if that translates to an experiment on the real devices. Once again, here we had Cisco switches in our lab, and we added at most 500 megarules on one of them. And we tried, once again, the most challenging assignment strategies of this random IP to ingress assignment. And first, note also that in the lab, our device could only sample at the rate of 1 in 4,000, so meaning that was the highest amount of samples we could get from the used S-Flow implementation there. So if we first only consider sample packets, we see a very similar pattern between simulation results that match the setup and the lab, but obviously our simulation is only an approximation of what really happens on the device. Allowing Magnifier to add up to 500 megarules greatly increases the amount of /24 subnets for which we had a validated ingress point. But the number is lower in the lab because it takes us more time to add and remove the rules compared to the perfect setting in the simulation. So note that with more mirroring rules, obviously we could increase these results even more. And during all these experiments, we never mirrored more than 1.4% of all the traffic, often much less. And in fact, in the paper, we do a direct comparison with another mirroring-based system called Everflow that could give some similar insights, which in our simulations generated more mirror traffic. There is also other approaches to solve this problem, for example, Flow Voyager, which is limited to the observation of sample traffic, but does some very similar inference strategies than what Magnifier does. And finally, more active approaches, for example, Ping Mesh, which is focusing on data center networks, are not easily applicable in an ISP setting where we do not control direct endpoints or devices in our network. So to conclude again, what I tried to show you today is that we designed a system called Magnifier, which works in multiple steps. So first, we do an inference based on the sampled observation, which covers much more traffic than what we see in the sampled packets only, therefore increasing our coverage. Then we use the mirror traffic to validate these observations, and we try to reduce the overhead in the form of mirror traffic that we generate, and also feeding back wrong inferences, which lead us to an increased coverage over time. But we should also mention here that obviously also the traffic moves over time. We will not continuously improve all the time because the networks are very fluent and things change over time. Finally, you might notice or have one question in mind. So what happens about the IP space that we never sampled to begin with? So then we cannot really do any inference steps and validations. So here you can argue, yes, it's probably so few traffic that it doesn't matter. But on the other hand, one extension could be that we reserve some mirroring space to kind of go through the IP space over time to figure out more traffic that enters or leaves the network. And with that, I'm happy to answer questions.